tackle section 3.2, which are applications of radian measure. And the good thing is there's only two main applications in here. We're going to deal with arc length on a circle and area of a sector of a circle. And so this section, unlike all of the sections that have come before it, they've all dealt with triangles. And if we've had any applications, they've been applications to write triangles. This is the first time we're really going to see any applications to circles. You probably did a little bit of this in geometry. I don't know how much. So I'm going to teach it as though you've never had it before. First thing we're going to start off with is arc length. We talked a little bit about it last time, what arc length is and all that good stuff. Basically, the length S, and for some reason in math, arc length is always represented by the letter S. I would have done capital, well, I guess capital A was already for area, huh? So I guess little s it is. The length S of the arc intercepted on a circle that has a radius of little r by a central angle that measures theta radians. And that's going to be your first important kind of note there. That the angle has to be in radians. It is given by the product of the radius and the radian measure of the angle. So basically, what do you need to take away from that? Well, we come up with this formula. Arc length is always equal to r theta. So S equals r theta, where S is the arc length, r is the radius of the circle in question, and theta is the angle in question, but that angle has to be in radians. So it's really important that you note that. This formula only works if you are in radians. Got it? Okay, so why are we so interested in arc length? Anybody know? As opposed to, why not just leave it as a triangle and do straight line distance every time?
Because in life there aren't always straight lines. Sometimes you have to go in an arc.
When mainly do we go in an arc?
Rotation.
Rotation. When else? Let's say I get in an airplane and I fly from here to
You don't go in a straight
Italy.
line.
Am I going in a straight line or am I going to fly in an arc?
In an arc because you're going over.
I mean, I'm going halfway around the world, or, well, maybe not halfway, but 7,500 kilometers or so, right?
You can't go
So,
straight.
yeah, you can't go straight.
You hit the Empire State Building.
There you go. Well, I don't even know. I might fly into outer space, right?
Yeah.
So we have to curve to stay within our atmosphere there. So it's really important in terms of navigation and things like that. If we're relatively close, if we're talking about 100 miles or so, that's not major arc length. You know, so maybe we can deal with triangles. But even that's getting to the point where you're at different latitudes and longitudes. So, you know, latitude, longitude, all of that's measured in arcs, as well as how airplanes travel. So this is a really important section. Okay. Just one more caution here. This formula only works if your angles are in radians. The biggest error is people just plug those angles in degrees and it doesn't work. So here's our first example. We have a circle that has a radius of 18.20 centimeters, and we would like to find the length of the arc intercepted by a central angle that measures 3 pi over 8 radians. So we've already drawn a little picture of it over here. You can see this, here's a circle, has a radius of 18.20 centimeters. We've drawn the angle, 3 pi over 8, and I'm looking for S, which is this distance right here. So basically, arc length is just a piece of the circumference. If you think about circumference as 2 times pi times the radius, well, when we start talking about it in terms of angles, you can hear those conversion factors coming in there.
So for this one, would we need to change it?
But let's look at our formula and talk about it, okay? All right, so what formula am I going to use to calculate arc length? S equals r theta. Okay, well, I'm looking for S. I know the radius, and the radius units don't matter. You use whatever are given. So we're going to use 18.20 centimeters. Now let's talk about that theta, because you asked. What did I give you theta in? Radians, not degrees. So if it's given in radians, you don't have to convert. You only have to convert if you're given a degree measure. So we're ready just to substitute in. So we're going to multiply that by theta, which is 3 pi over 8. And that's radians. Now, I want you to multiply those together, but I want you first to leave it as a number of pi. Okay, so leave it exact at first. So 18.20 times 3 divided by 8 is what? Give it to me as a fraction. Give it to me exact.
273 over 40.
Did you guys get 273 pi over 40? Okay, that's the exact value. And the reason I bring it up is this is how the ACT will typically leave it. They're going to leave things exact because technically on the ACT, you don't even need a calculator, or so they say. They try to give you those that you could do by hand. So that's the exact. Now, I don't really know how many centimeters that is. That's 273 pi over 40 centimeters. To me, I would like to do that in terms of significant digits as well and get an approximation so I kind of have a feel for what that is. So let's go ahead and let's now type that pi in, 273 pi over 40, and let's turn it into a decimal. Did you guys get 21.44136986? So when we actually type that in and convert it to a decimal, we got 21.44136986 centimeters. Okay, so there it is as a decimal to as many places as my calculator can handle. How many significant digits should I have here?
1.
How many does this guy have?
4.
That one has 4. And then I'm going to go ahead and tell you that anything with pi in it is considered exact, and it does not play into your significant digits. So you don't use this number at all. That's understood to be exact. So the only one determining your significant digits is 18.20. So we're going to give it to 4, which would be 21.44 centimeters.
Is that the one you want us to put down?
I'll usually tell you. I'll tell you whether to leave it exact or to, do significant digits. Or sometimes I'll just say round to the nearest tenth or something like that. So just pay attention to directions, and if you're unsure, just ask. Okay, let's stick with that same circle. Let's let it have a radius still of 18.20 centimeters. But now let's find the length of the arc intercepted by a central angle that measures 144 degrees. So I'm going to go ahead and draw the circle over here just so we can talk about it. Here's my circle. Here's my radius. And then I want 144 degrees. Well, if I went all the way around to here, that would be 180, right? So that's probably, I don't know, about, what do you guys think? About right there? Okay. So that's 144 degrees. I want to know how far it is from here around to here. So anytime I'm dealing with finding a portion of the circumference, I'm dealing with arc length. So we're going to use the formula S equals R theta, 18.20 centimeters multiplied by theta. Now here's where we get into trouble. The theta I gave you is in degrees, but to work this problem, you have to do it in radians. So we're going to go off to the side and we're going to convert that angle into radians. So do you remember your conversion factor for converting to radians? You multiply by pi over 180 degrees. So we're going to multiply by pi over 180 degrees. The degrees will cancel. And let's just simplify 144 divided by 180 and turn it into a fraction. It's what?
4 over
4/5 of pi? Okay. So that converts to 4 pi over 5. Did everyone get that? Okay. So that's really what, about 80% of a pi? Yeah. Okay. That's what we're going to substitute in. If we substitute the 144 in, we're not going to get it correct. We have to use the radian measure. So we'll put 4 pi over 5 as our radian measure, and then we'll clean that up. First we'll write it exactly. So let's see what we get there. 18.20 times 4 divided by 5 gives me, did you guys get 364 pi over 25?
Yes.
Okay, 364 pi over 25, and that's the exact value of the centimeters. It's probably what you would see on a standardized test. however, am going to find it approximately and round to 4. No, in this case, not 4. How many significant digits? Just 3, yeah. This one has 4, but this one only has 3. So we'll go to 3 significant digits for this one. So let's turn that into an actual decimal. I got 45.7415. Anyone else? Yes? 45.74158904 centimeters. And to 3 significant digits is 45.7 centimeters. So there's the basic calculation of arc length for circles.
Because I was in his class.
Okay, so for this example, we're going to talk about latitude. Latitude gives the measure of a central angle with a vertex at the Earth's center, whose initial side goes through the equator and whose terminal side goes through the given location. So Reno, Nevada is approximately due north of Los Angeles. We know the latitude of Reno is 40 degrees to the north. To the north of what? The equator. Latitude is always given with respect to the equator. So 40 degrees to the north, and Los Angeles is 34 degrees to the north of the equator. The radius of the Earth is about 6,400 kilometers. We would like to use that information to find the north-south distance between those two cities. Okay, so let's see if we can get an idea of what's going on here. Here's the Earth. What's the radius of the Earth? About 6,400 kilometers, right? Okay, so 6,400 kilometers. So here's the equator. I've drawn it up here, and I'm using that as my radius. Then if I measure 40 degrees north of there, that would be 90, so 40 would be about right here. What sits there? That's Reno, right? That's Reno right there. Los Angeles is not really that far from there. It's about right there. This is LA. Okay? So Reno is 40 degrees north. Los Angeles is 34 degrees north. My question is, what is the angle between them? 6 degrees. So we understand that because they're in the same direction, I only want to find this little bit right here of arc length. I want to know that. I want to know that distance right there. So that's all the arc length I need. So I need the angle between them. So we're not going to use the 40. We're not going to use the 36. I'm sorry, the 34. We're going to subtract them and find the angle between them.
Which is 6.
Between them is 6 degrees. So that's our theta. That's how we get started. The angle between them is 6 degrees. But can I use that to find arc length? I need to convert it to radians. So I'm going to multiply it by pi divided by 180 degrees. And I'm going to change that 6 degrees that I found to pi over 30 radians. And that turns out to be the angle between those two cities in terms of latitude. There's a 6 degree change in latitude between Los Angeles and Reno. I've driven there, by the way. To Los Angeles. It was fun. About, I don't know, about 32 hours maybe of driving to Los Angeles. We did it 2 summers ago. It was really neat. And then we went to San Francisco and to Yosemite from there. Okay, so we have S equals R theta. In this case, we're talking about the radius of the Earth, so about 6,400 kilometers. And we're going to multiply by the angle between them. The angle between those two cities we found to be 6 degrees, but as a radian, pi over 30. All right, give that to me exactly.
640 pi over 3.
640 pi over 3. And that's how many kilometers it is exactly. Now let's round that to a decimal. We take the 640 and we actually multiply it by pi and divide it by 3. We get, did you guys get 670.20?
670.
kilometers it is. That's how many kilometers Reno is north of Los Angeles. Let's see how many significant digits the original problem gave. The original problem only gave us how many? 1. So, you know, technically I guess we should round that to what?
700.
About 700 kilometers.
And I think that's kind of.
You know, ballpark. We could have been more precise about lots of things. The radius of the Earth, we could have measured those angles a little more precisely, but we didn't. So we're stuck with 1 significant digit. That's kind of neat, don't you think? So when you think about like the way distances are calculated on a map, you actually get kind of a skewed version of the map when you think about it than if you just broke out a ruler and calculated and did the scale. But they also, the way the map has been flattened, they've done it the best way they can to try to make it look as realistic as possible, you know, because they've flattened it out, which is kind of cool. All right, there's a good spot for us to kind of break, and then we'll do the rest of this.